We acknowledge the first Australians as the traditional custodians of the continent, whose culture is the oldest living culture in human history. We pay our respects to elders, past, present and emerging, and we respect their cultural heritage, beliefs and relationship with the land. We extend our respect to all Aboriginal and Torres Strait Islander people here today. They share the memories, traditions and hopes of the traditional ancestors with the new generations today and in the future. We would also like to thank them for looking after this land for thousands of years.
Good afternoon, everyone, and welcome to our second SciFest session for today. We're very excited to have Julie from ANSTO here to present in their element. There's going to be some questions coming through from Julie that if you can put your answers in the chat for that, and there'll be time for some more formal questions at the end. So please put those in the Q&A. And I'm going to pass you straight over to Julie to get into this fabulous session all about elements. So thank you so much, Julie.
And thank you. So good afternoon, everyone. As you heard, I'm Julie and I'm an Education Officer at ANSTO. So what is ANSTO and what is it that we do at ANSTO? Well, ANSTO specialises in science at tiny scales, at the level of atoms and even smaller. And we're all about nuclear science. That is the science of the atomic world. So I'm going to introduce you to the world of ANSTO. Just let me share my screen. And let me introduce you to the world of ANSTO.
You're about to go on a journey into the atomic world, a world that forms the building blocks of everything in the universe, from the unimaginable distances of space to the wonder of the world around us. We are formed from complicated components far, far smaller than the eye can see, from the billions of different cells that make up the myriad of life on this planet, to the DNA that forms the blueprint to our genetic code, and further into the atomic world. Here, electrons travel just under the speed of light. Protons and neutrons are bound strongly together with nuclear forces. Billions upon billions of atoms fit into a space no larger than the head of a pin. Welcome to the amazing world of ANSTO. Our journey begins here at Opal, Australia's only research reactor.
So this particular presentation is accompanied by a worksheet that you might like to have a copy of and might like to complete throughout the presentation. So as I said, as the video said, we're all about nuclear science, and that's the science of the atomic world. And atoms are the fundamental constituents of everything around us, and we ourselves are entirely composed of them. So nuclear science is crucial for understanding our universe, our world, and ourselves at the atomic level. If we can understand how atoms come together, interact, and can be combined with other atoms, then new, more efficient materials and medicines can be developed. So at ANSTO, we are the home of Australia's most significant landmark and national infrastructure for nuclear science research. Firstly, we're the home of Australia's one and only nuclear reactor that you can see in the top left-hand corner there. Our reactor is called OPAL, and that stands for Open Pool Australian Light Water Reactor. And the purpose of OPAL is to produce lots and lots and lots of neutrons. and it produces those neutrons from splitting atoms of uranium in two. Now, those neutrons are channeled down beamlines into the Australian Centre for Neutron Scattering that you can see in the top right-hand corner. Here we actually have 15 instruments that can use those neutrons to see inside materials down to the atomic scale. We also have an Australian Centre for Accelerator Science, that you can see in the bottom left-hand corner. And here the machines use magnets and electric fields to separate atoms from a sample according to their mass. In the bottom right-hand corner, you can see that we have the Australian synchrotron. Now, this is actually located down in Melbourne, and it accelerates electrons close to the speed of light and uses the radiation that comes off them to see inside materials. Now, I know that we're all learning about atoms, so let's take a closer look at atoms. What you see here on the screen is a circle that represents the electron cloud of the atom. Now, you can see from the scale down the bottom that it's really, really small. It's only 0.1 nanometers in distance. That is 1/10,000,000th of a meter. Now, the nucleus, which you find at the center of the atom, that's even smaller. It's 1/10,000th the width of the atom. So this means that an atom really is mainly empty space. So to put an atom in perspective, if you lined up atoms across the width of a human hair, how many atoms do you think might go across that width? You might like to type an answer into the chat. If you look at the human hair, so I know you're all thinking, and if you look at the human hair, there are 1 million atoms that could, 800 billion was an answer, but there are 1 million atoms that can line up across the diameter of a human hair, 1 million. Okay, so to get our minds around the actual size of an atom and how big the nucleus is compared to that atom, we're going to see if we blew up, imagine if we blew up an atom to the size of a football stadium. The one shown on the screen is Stadium Australia, currently where the Women's World Cup soccer is being held. So if we blow an atom up to the size of that stadium, so that the electron shell would be the size of the stadium, and the nucleus would be in the middle, how big do you think the nucleus would be? Do you think it would be the size of a small car? Do you think it would be as big as you? Do you think it would be the size of a football? The size of an orange? The size of a soccer ball? That's a good guess. The size of a golf ball? Well, guess what? All of those things I've said are actually too big. It would only be the size of a small grape or a small marble. Now, let's consider the atom some more. The most powerful electron microscopes can actually create images of individual atoms. But how do we know of the particles that atoms are composed of? Well, scientists in the early 1900s were able to infer a lot about the structure of an atom and to propose models of what an atom might look like from the experiments that they performed to investigate the structure. The most commonly used model today is based on a model developed by the scientist Niels Bohr in 1913. And this is the model that you can see here on the screen. So you're probably very familiar with this model. Now, in the center, you can see we have the nucleus. We've been talking about the nucleus. And that nucleus is composed of two different types of particles. Now, I'm sure you know those particles. The positive ones are called protons. And the ones that have no charge, you can see in the center, those blue ones, they're called neutrons. Now, protons and neutrons together are given a name. They're called nucleons because they're found in the nucleus. And they make up virtually all the mass or weight of the atom. Now, the particles that are spinning around the outside with that negative charge you can see there, they're called electrons. And they exist on the edge of spheres called electron shells. And each shell can only hold a certain number of electrons. And the shells have to be filled from the inside out. So in order from the one closest to the nucleus out from the nucleus. Now, as you can see, only 2 electrons can fit in the innermost shell, whereas up to 8 electrons can fit in the second shell and up to 8 electrons can fit into the third shell for the first 20 elements. Now, an atom is the smallest part of a chemical element that can exist. So we can find out which chemical element this atom is by counting up the number of protons in its nucleus. So you can count the number of protons now and see if you can work it out. I'll ask you later on which element it is, and you can type it in the chat. We can also determine the atom's weight or atomic mass by counting up both the number of protons and the number of neutrons in the nucleus of the atom. And this is because a proton and a neutron weigh about the same. As you can see from this table here, they weigh about 1 atomic mass unit, whereas electrons, they only weigh 1/2000th the mass of a proton or a neutron. And so when we're determining the mass of an atom, they are basically insignificant. Okay, so have you worked out what atom it is? So the number 9 was the number of protons in the nucleus. I'm sure that's what you all got. And that's called the atomic number. The number 19, that's the atomic weight. That is the total number of protons and neutrons in the nucleus. So can anybody guess what element it is? Okay. I'm looking at I haven't got any answers in the chat. Not oxygen with number 9, fluorine. That's exactly right. It's fluorine. So it's the element fluorine. Now, each of our elements, they are represented by a symbol. And the symbol is given, the symbol is actually universal. So all across the world, everybody recognizes the elements by their symbol, even if they call them a different name. So in general, the symbol is the first letter of the name of the element, and that's written as a capital letter. But if that's often being used, you also include another letter from the element's name. But for fluorine, it's just F. Now, how did we know which element it was? Well, all of the elements that we know, they're listed on a table, which is known as the periodic table. And yep, that's the chart that you see in the walls of this, just about every school science laboratory. Now, the elements are listed in our periodic table in order of the number of protons in the nucleus of their atom. So in the periodic table today, they're listed according to the number of protons in the nucleus of the atom. So number 9 has 9 protons, and that is fluorine. Now, how many elements do we currently have on our periodic table? Any guesses? How many elements do we currently have on our periodic table? Yep, 118. That's exactly right. We have 118. And in fact, the last 4 elements, that is 113, 115, 117, and 118, they were only added to the periodic table in 2016. So, did we always know most of the elements that are listed on our periodic table? And how did our periodic table come to be? To answer these questions, we're actually going to explore a little bit of the history of the elements. So I'm going to share with you another screen. Now, only about 11 elements, 11 were known in ancient times, and that is before the fall of the Roman Empire, around 476 current era. The first metal to be discovered is shown on your screen, and I'm sure you can all guess what it is. Yep, it's gold. That's exactly right. So How might you find gold? Think about the gold rush in Australia. What were they actually looking for? Well, you're probably thinking they were looking for nuggets or small pieces of actual gold in the river sand. So gold can be found naturally as lumps of almost pure metal. Another metal that was used in ancient times was copper, and I'll put that there too, and you can see that. Copper can also be found as lumps of native copper, and both these metals were initially used for making jewellery, ornaments and tools. What properties of these metals would make them useful for making these objects? Anyone? What property would you have to use to make jewellery or to make ornaments or to make tools? I'm sure you're all thinking, yes, they're malleable. Excellent. Malleable means that if I hammer them, they can be beaten and bent into various shapes. The other thing they have is metallic luster. They're shiny, and that makes them really nice for ornaments and jewellery. But these metals were fairly rare, and so the items that were made from them in ancient times were prized possessions. Egypt is a land rich in gold, and the ancient Egyptians excelled in the manufacturing of gold, and it has a strong presence in their life. Now, treasures that were found in Pharaoh's tombs indicate the high degree of mastery that the ancient Egyptian goldsmiths had. The sarcophagus, or innermost coffin, of one of the most well-known pharaohs, Tutankhamun, was made entirely of gold, and it weighs 110 kilograms. Copper beads have also been excavated in northern Iraq, and they've been found to be over 10,000 years old, and they're presumed to be made from native or natural copper. But copper's generally found in ores of copper compounds. And in the Middle East, around 5000 BCE, humans discovered that it was actually easy to extract copper from its naturally occurring compounds or minerals. You just had to roast the minerals in a fire. Now, another element that we're going to have a look at that was also known in ancient times is lead. And again, it was known because of its ease of extraction from its ore. It's believed that humans have been using lead for over 6,000 years. The ancient Romans were actually very big users of lead. They used it in cosmetics, they used it in coins, they even used it for their water pipes and their tableware, which is a bit of a problem because lead's actually highly toxic. The effects of lead poisoning were actually recognised in ancient times, but it wasn't until the 20th century that we had laws that affected the use of lead in order to protect people's health. Before this, lead was widely used in paint, and it was used in cosmetics, and it was also in petrol. Some old houses in Australia have lead paint on their walls, and renovators, they need to take precautions when removing it. And lead petrol was only completely phased out in Australia on the 1st of January 2002. And there was one famous user of white lead makeup, and that was Queen Elizabeth II, because she believed that the white paint made her look young. Now, lead is a very high density metal, and that makes it useful for shielding against X-rays and gamma radiation. So at ANSTO, we use lead pots to transfer radioactive material around our site. Now, another element that was known in ancient times that looks very different to the other three elements that I've just shown you was sulfur. You might recognise sulfur because of its yellow colour. It was also known as brimstone in ancient times, and it was commonly found in its elemental form in volcanic areas. If you've ever been to a volcanic area, you'll know that these areas often have a distinctive smell, and they smell like rotten eggs. And that's due to a small amount of hydrogen sulfide gas that's produced. Now, sulfur was used by the ancient Greeks for bleaching cloth and for preserving wine. It still is used for preserving wine today, both of which involve burning sulfur to form sulfur dioxide and allowing this to be absorbed by the wet clothes or the grape juice. Now, I said that sulfur looked very different from the other elements that you can see there. Gold, copper, and lead, they are all metals. But sulfur is a non-metal. In other words, it's not malleable. If you hammer it, it's brittle and it will crack and split. Now, why do you think that these elements that you can see there were the first elements to be discovered? Well, if you've been listening, it's because they could be found in their native form, or they were easily able to be separated from their ore just by heating the ore in a fire. Now, the other thing you'll notice, if you're having a look at the elements that I'm showing you there, is that their symbols that you can see on top of the pots don't actually match their names, not like the symbol fluorine, which seemed to match the element name. Why don't you think they match their names? Anyone know? Why do they have different symbols to their names? The symbol for gold is AU, whereas the symbol for lead is PB. Why is that?
Someone put in the Q&A that it could be Latin.
Perfect answer. That's great. It is Latin. Yes, because these elements were known in ancient times and they were given different names in those times. In fact, gold was called aurum. Now you can see where it gets its symbol from, aurum, AU. Copper was known as cuprum, so therefore cuprum, CU. And lead used to be called plumbum, and so its name, its symbol is PB. And in fact, do you remember me saying that the lead was also used to make the water pipes in ancient Rome? So the name for people, for an occupation that works with water pipes, is plumber, because it comes from the name for lead, plumbum. Now, sulfur comes from the Latin sulfurium or the Sanskrit solver, and that's where it gets its symbol from. Now, another element that was discovered in ancient times was tin, and you'll notice that tin also has a symbol SN that doesn't relate to the word tin, and that's because in ancient times it was known as stannum. The discovery of tin is really important in human history because when copper is mixed with around 5% of tin, it produces an alloy or a mixture of metals called bronze. And bronze is much, much harder than copper, and it's ideal for tools and for weapons. So the Bronze Age is now recognized as a stage in the development of human civilization. And nations that first developed this technology to make bronze weapons soon conquered their less developed neighbors. Another element that was known in ancient times that we're going to look at, again, that has a symbol that doesn't relate to its name, is iron. And that's because it used to be known as ferrum. And so the symbol Fe comes from ferrum. Now, it's been around a long, long time because it can be found as an element, a pure natural element, in some meteorites. But of course, to find it in that form is very rare. So unlike copper and tin, which could both be easily extracted from their ores just by roasting the ore in fires, iron actually required much, much higher temperatures. So it was the ancient Hittites of Asia Minor, which is today's Turkey, who were the first to smelt iron from its ore around 1500 BCE. They heated the ore in a fire, but they blew air to fan the fire, and they heated the ore with charcoal, which is a form of carbon. So they heated the ore at very high temperatures with this carbon, with this charcoal, and they were able to extract the iron. Now, the new, stronger metal could produce weapons such as swords, and it gave people who had this technology economic and political power. So the Iron Age is recognized as another stage in the history of human civilization. Now, the ease with which these metals could be extracted from their ore by, say, heating just in a fire, or by heating them strongly with a lot of heat in a fire, it's related to the activity of the metals. So we're going to take a look at the metals that we've discussed so far. So you should be able to see this sheet here. Now, gold was actually able to be found in its natural state. It still can be found in its natural state, very small amounts. But copper could also be found in that way. Here we go there. But also copper is found in compounds in ores, but to extract the copper from the ore, it just needed to be roasted in a fire. Similarly, lead and tin could be extracted from their ores just by roasting the ores in a fire. But when we get to iron, it requires a lot greater temperature, and it also requires blowing air into the fire to increase the temperature and heating the ore with charcoal to actually extract the iron. So what you see is that the metals that you can see to the left or to the right, the ones that are least reactive on that side, they are the ones that were most easily extracted from their ores, and they are less reactive metals. And the reactivity increases as you move across towards iron, where the metal is much more difficult to obtain from its ore. Now, there's one other metal that you've got in your worksheets that we haven't spoken about yet, but we're going to be getting to that. So from the discovery of the first elements until about halfway through the 18th century, now that's over 8,000 years after the discovery of gold and copper, only 15 elements were known at that time. So for 8,000 years, only 15 elements were known. Basically, the way of discovering a new element was to do stuff to a substance that you thought contained new elements. You melted them. You heated them at high temperatures by blowing air into the furnace. You added acids. You added other substances. And maybe you heated them again to see if you got something new from it. So over the next 50 years, between 1750 and 1800, the number of known elements more than doubled, as another 18 elements were discovered during that time, taking the known elements to 33. Now, one of those elements that was discovered during that time was molybdenum, and that's a really important element for us at ANSTO. So, you can see the molybdenum there. Molybdenum was discovered in 1778 by Carl Wilhelm Scheele, and he's a Swedish chemist. Now, remember I said that you had to do a lot of things to be able to extract these compounds? Well, what he did, he found this, he extracted molybdenum from a mineral now known as molybdenite. He managed to produce a substance from molybdenite called molybdic acid, and then he mixed the molybdic acid with carbon and ground it together in linseed oil to form a paste, and then he heated that to a red heat, and lo and behold, it produced molybdenum metal. Molybdenum is actually an essential element in all plants and animals, and more than 50 molybdenum enzymes are known. Now, at ANSTO, we produce radioactive molybdenum-99 in our opal reactor, and that decays to form another radioactive element called technetium-99m. And that technetium-99m is the most widely used medical radioisotope in the world. It's used in 85% of nuclear medicine scans here in Australia and around the world, and that accounts for 45 million scans around the world every year. Now, ANSTO is one of a handful of reactors that are producing that molybdenum-99 for the global supply of that vitally important medicine, technetium-99m. Technetium-99m can be used to diagnose so many problems in the body, problems with your heart, with your brain, with your lungs, with your liver, with your kidneys, and even with your bones. Now, what chemists could actually do to break down compounds, chemists could do to break down compounds and isolate elements was actually limited to the technology that they had in the day. So in 1800, the first battery was invented by Alexander Volta. So before 1800, there was no electricity, not even battery electricity. It was now after 1800 that chemists could use electricity to break down compounds. And this was actually needed to discover the more reactive metal elements. And the first one to do this was Humphrey Davy. In 1807, he used strong heat to melt the compounds, and then he used electricity to separate the elements out of their molten compounds. And in this way, he discovered the elements of sodium, potassium, and calcium. Now, we don't have any of those because they're so reactive with sodium, potassium, that you need to keep them under some oil so they don't react with the air. But what we do have is a common element that you see at school, which is magnesium, because he also used this method to isolate a pure sample of magnesium by putting electricity through molten magnesium oxide. Before Davy, only an impure sample of magnesium had ever been isolated. Now, in the next 50 years, another 25 elements were discovered. So you can see the discovery of elements after 1800 is running forward, racing on. And so by the middle of the 1800s, there were 58 elements known. So another element that's important to humankind was discovered in the early 1800s was silicon. And you can see some silicon here on the screen. So silicon is the second most abundant element on Earth after oxygen. Beach sand is actually silicon dioxide, a compound of silicon and oxygen. Now, the credit to discovering silicon goes to the Swedish chemist Berzelius of Stockholm in 1824. Now, he was able to extract silicon by adding potassium to a compound that contains silicon. And that was only possible after Davy had discovered how to get potassium, that's a reactive metal, using electricity. So you had to have electricity and then Davy to extract potassium from the compound of potassium for Berzelius to be able to discover silicon. Now, silicon's an interesting element because neither a metal or a non-metal. It's classified as a semi-metal because it has the properties of both metals and non-metals. So you can see, if you have a look, a property of metals that silicon has. It's actually shiny, just like metals. Can you see that there? It's shiny. But it doesn't conduct electricity. And if you were to pick up a piece of that silicon and hit it with a hammer, it would actually break and crack. And that's because it's brittle, not malleable like metals. Now, but silicon's one of the most useful elements to mankind because it's an element to thank for your computer. It's a crucial component in microelectronics and computer chips. And ANSTO uses its opal reactor to improve the conducting properties of silicon by introducing phosphorus impurities into the crystalline lattice through a radiation of silicon with neutrons. In fact, we irradiate 6% of the world's silicon, but we make 60% of the world's ultra high quality silicon semiconductor material that's used in high-end electronics for satellites and for the electric vehicles that we're getting produced today. And it's also used in the electronics for wind and solar energy. So I'm going to resume the PowerPoint now. Because we've talked a lot about the discovery of elements, that is the 11 elements that were known, as you can see here on the screen in ancient times, and then the elements that were discovered because we started to get a race on in 1750 to 1800, and then some that were discovered just after that. But at this stage in history, the early 1800s, these elements were just random new substances, all like that on the screen. And scientists don't like having random things that they don't have any order to. They always like looking for patterns and trends and ways to order and classify things. So it was around this time, the early 1800s, that attempts were made to rearrange the elements in some way by looking at their physical properties, That is what they look like, their appearance, their melting point, how they, their solubility, whether they dissolved in water, and their chemical properties, how they burnt in air, their reaction with acids and other substances. Now, although there were quite a few attempts at organizing the elements, it was Dmitry Mendeleev in 1869 who was the most successful. He's often called the father of the periodic table. Now, believe it or not, he actually came up with the periodic table when he was facing a deadline for a second volume of a chemistry textbook that he was writing, and he wanted to publish something new about the elements for his students. In Mendeleev, in 1869, when he was looking at his periodic table, there were only 63 elements that were known. So he arranged these elements from lightest to heaviest. He started a new row, because you can see he's got a table there, whenever the properties of the elements appeared to resemble those in the row above. And so he placed the elements which had similar properties, similar physical and chemical properties, under one another to obtain rows. Now, an English chemist, John Newlands, he'd actually done this before, this exact same thing. But Mendeleev's genius was in what he left out of his table. He recognized that certain elements were missing and they were yet to be discovered. So he left gaps in his table. And you can see these question marks here. When the next element that he had to place didn't actually fit with the other elements in the column, meaning that its properties were not similar to those elements above it, and it didn't belong to that group. And he was even able to predict the properties of the elements that he said were missing, and this was Mendeleev's brilliance. So, as I said, have a look at those question marks, and we're going to focus on the question mark that's under aluminium, a space that he left for an unknown element. Now, not only did Mendeleev suggest that this element actually existed and that we actually hadn't been able to find it yet, he also predicted the properties of this element. And you can see that on the right-hand side. He predicted that it would have an atomic mass of 68, it would have a density of 6.0 grams per cubic centimetre, and it would have a low melting point. Now, he challenged us, didn't he? He said, well, there's an element that's missing, you need to go and find it. So 6 years later, in 1875, Paul-Émile de Boisbrand isolated an element that he called gallium, and he determined its properties. So look how close the properties of gallium are compared to the properties that were predicted by Mendeleev for Eka aluminium. And you can see those properties. Density of 6, the density is now known to be 5.9. Low melting point, it's got a melting point around 30 degrees C. Valency of 3, and method of discovery, probably by its spectrum, and it was discovered spectroscopically. So how amazing is that? And that element slotted directly into the space left in Mendeleev's periodic table. Now, we actually have a sample of gallium here, so I'm just going to show you that. Here is a sample of gallium here. Sorry. So you should all be able to see it there. Now, if you have a look at it, you can see it's a soft, shiny, silvery white metal. So it's a bit like the color of aluminium, it's in the same column as aluminium, same chemical group as aluminium. So I've actually been heating a sample of gallium in a container for the last 20 minutes. And if you look at my container, I'm just going to show you and move these slightly out the way. Can you see that when I shake it or tip it, touch it, you can see that it moves, it shimmers, because I've made it a liquid just by using my body temperature. So you can see that it's a liquid. Can you see that when I tap it? You can see it move. like that. So that means it's gone from a solid to a liquid at a very low temperature, at around 30 degrees. So my body temperature is 37 degrees, and I've heated it and managed to melt it. So for a metal element, that's a very low melting point, 30 degrees C in there. So similar were most of the experimental findings of de Boisdobran to Mendeleev's actual predictions, that when Boisdobran stated he measured the density for the metal at 4.5 grams per cubic centimetre, and guess what? Mendeleev went, well, that's not right. I say it's 6 grams per cubic centimetre. And he was so convinced that he was right that Mendeleev was compelled to write and suggest that Boisdobran had got it wrong. And indeed, the value has subsequently been corrected to 5.9 grams per centimetre cube, in stunning agreement with Mendeleev's prediction. Now, Mendeleev did the same for scandium, germanium, and technetium. And technetium wasn't discovered until 30 years after Mendeleev's death in 1937. How amazing is that? So I'm just going to share the PowerPoint again, because we're going to actually have a look now at our modern periodic table. And it definitely looks very different to the one that Mendeleev proposed. However, his ideas, as I said, he's known as the father of the periodic table because his ideas are the basis of our modern periodic table. So we now know a lot more about the structure of an atom and how this relates to its chemical properties than he did. When Mendeleev was doing his work about the structure of the periodic table, atoms were thought to be tiny, indivisible particles. The parts of an atom, that is the existence of a proton and a neutron and electrons, they weren't discovered until the late 19th and earlier 20th century. That is around the start of the 1900s, over 30 years after Mendeleev came up with his periodic table. So for such an important table, it seems to have a very quirky layout, but that's because it's set out to show us two of the most important things about atoms of any element: the number of protons in the nucleus and the number of electrons that are buzzing around outside in the outermost shell. Now, the table is called the periodic table because the elements show patterns in their chemical properties at certain regular intervals, leading to rows and columns of the table. So we're going to have a quick look at those patterns. As we know, the elements in our periodic table are not arranged according to the atomic mass. They're actually arranged according to the number of protons in the nucleus. You can see here in the top left-hand corner of each of the elements. So that's because we now know that the number of protons in all atoms of the same element is constant, but not the atomic weight, as every element has naturally occurring isotopes. That is, they have atoms that have the same number of protons in their nucleus, which is the constant part of the atom, but they can have different numbers of neutrons in their nucleus. The elements are also arranged in rows, which are also called periods, according to the outer electron shell that's being filled. So in the first row that you can see here, we have 2 elements. That's because the first shell of the innermost shell of an atom can contain up to 2 electrons. In the second row, we have 8 elements. That's because the second electron shell can contain up to 8 electrons. And the third row we have has 8 elements, and that's again because the third electron shell can contain up to 8 electrons for the first 20 elements. So we're now actually going to have a look at the elements as you go across a row, and we've chosen period 3 to investigate. So if we go across the row, you can see that we have elements on the left-hand side that are metal elements. And then if you look at, we go across to silicon, and silicon's classed as a semi-metal element. And on the right-hand side, we have the elements that are non-metal elements. So looking at their physical properties, we're going from metal all the way across to semi-metal and then across to non-metals. So the elements are becoming less metallic as we go across a row. Now let's have a look at the columns of the periodic table. So the columns, because to locate an element on the periodic table, not only do we have to know which electron shell we're filling, but we also, which gives us the row, but we also need to know the number of electrons in its outermost electron shell, because that determines the vertical column or group that it belongs to. So I'm going to start with the noble gases, which you can see here. You might have noticed that these elements weren't included in Mendeleev's periodic table because they weren't discovered until the late 1890s, though they weren't known when Mendeleev was developing his table. And this is because they only exist in very tiny amounts in the Earth's atmosphere. And their atoms have full, complete outer electron shells, so they don't readily combine with other elements, and they're found as single atom molecules in the atmosphere. Now, another group that we have are group 2 that I can show you. And these are a group of silvery, shiny, and relatively soft metals. And they have 2 electrons in their outer shell, and that's why they're called group 2. And they're fairly reactive metals. But if we look at elements as we go down a group, we're going to look at group 5. And you can see at the top, we're starting with nitrogen and phosphorus, which you'll know are both non-metals. And then we have arsenic, which is a semi-metal. And then down the bottom, we have bismuth and moscovium, which are both metals. So as you go down the group, you can see we're going from non-metals to semi-metals to metals. So they're becoming more metallic as we go down a group. Well, that's the end of our presentation for the moment, and I'm not sure whether we actually have time for just a little bit of a game. Do we have time for a little bit of a game?
I think we have a couple of minutes. If any of the participants do need to head off, thank you for joining us. But yes, we've got someone in the chat saying yes. So let's do the game, and we'll finish off after that.
All right. I'm going to give you some clues, and what you have to do is write down or put in the chat which element you think it might be. You'll need a periodic table for it, so I'm just going to put up the periodic table that you can see, and that you can see on the screen. And you might also have a copy of a periodic table if you've got one. So my first one, who am I? I'm radioactive. Second clue, I was named after a country. Third clue, I have properties of both metals and non-metals. So what does that make me? Okay, see if you can guess. Oh, we've got some Californian. Oh, very clever guesses. Very clever guesses. Americium and germanium and uranium. Okay. Another one. I was discovered by Marie Curie. Any other guesses? Oh, we're getting some really good guesses here. Okay, no, haven't got it yet. I am in the same group as oxygen on the periodic table. As oxygen. Not curium, that's very good. That was named after Marie Curie. So we're in the same vertical column as oxygen. And we've got a radioactive symbol on us. So which one are we? Polonium, well done. Yes, she named polonium after her native country, Poland, because Poland wasn't in existence at that time. It had been swallowed up in the empire, an empire. Forgotten the name. Okay, one more question. Okay, here we go. All right. This time I'm going to give you 5 clues, and you've got to write down the names of the elements. So 5 clues, and each clue is an element. See if you can write down which elements I'm referring to. My atom has 8 electrons. My atom has 8 electrons. Next one. So write them down and then put them in the chat at the end. Okay. Someone's got it already. I am important for strong bones and teeth. So second element, I'm important for strong bones and teeth. Yes. Third element, I am a group 1 metal and I'm used in batteries for laptop computers and mobile phones. Fourth one, yep, I am found on match heads. And the last one is I make table salt when I am reacted with chlorine. Oh, Sakina, you are well done, and Shaky, well done. So very good. So oxygen, calcium, lithium, phosphorus, and sodium. Excellent. Well done. Very good. That's excellent. Thank you so much for joining us. I really enjoyed having this this afternoon. Thank you very much.
Excellent. Thank you so much, Julie. And well done, everyone, for all of those fabulous answers with those quiz. And for those of you that might be joining us on Friday for our molecules and atom trivia, you may have a bit of an advantage over some of the other participants. And yes, we will be sending out the recording. Hopefully you will have it tomorrow morning. Julie, would you just be able to unshare your screen for us, please? And we will do a big thank you. Excellent. So thank you so much for participating in this. And I have to say, I have listened to this session before, but every time I do, I get some new information out of it. So I certainly feel it's a wonderful way to start SciFest, starting at those building blocks of life. So yeah, all of the sort of molecules and atoms so important, and the history of them as well. So thank you very much for sharing all of that wonderful knowledge. And for everyone that has joined us today, just remember, this is only day 1. We have a liquid nitrogen show coming up at 4 o'clock today, and a whole host of programs for the rest of the week. So thank you so much, and a big thank you to Inspiring Australia, who enables us to put this event on every year. So thank you to everyone, and we look forward to seeing you all again soon.
Thank you very much.
This initiative is supported by Inspiring Australia New South Wales as part of National Science Week, and brought to you by Virtual Excursions Australia. Thank you, and join us for some more exciting sessions for SciFest 2023.